Semiconductor equipment manufacturing KPIs. In semiconductor manufacturing, tracking the right key performance indicators, or KPIs, is essential for achieving operational excellence. 4 critical KPIs provide a clear picture of equipment and process performance. The first is OEE, or Overall Equipment Effectiveness, which combines availability, performance, and quality to assess how well equipment is utilized. Next is yield, which represents the production quality rate, measuring the percentage of non-defective units produced. Higher yield means fewer reworks and scrap, directly impacting profitability. Cycle time reflects process speed, indicating how long it takes for a wafer to move through the production steps. Reducing cycle time improves responsiveness and reduces bottlenecks. Lastly, throughput measures production volume, showing how many wafers or units are completed within a specific time frame. Together, these KPIs form the foundation of performance measurement and optimization in semiconductor equipment manufacturing. What are KPIs? Key performance indicators, or KPIs, are measurable values that help determine how effectively an organization is meeting its business objectives. In manufacturing environments, KPIs serve as quantifiable metrics that guide decision-making, operational adjustments, and overall strategy. These indicators are especially crucial in semiconductor manufacturing, where precision and process control are paramount. KPIs provide real-time visibility into critical aspects of production, including performance, quality, and efficiency. By continuously monitoring these metrics, organizations can identify trends, detect deviations, and respond quickly to any inefficiencies. This allows for smarter resource allocation and supports ongoing improvement. Ultimately, KPIs are not just numbers, they are targets tied directly to performance outcomes. They help teams stay focused, aligned, and accountable as they strive to meet productivity and quality goals. Accurate, timely KPIs are foundational to achieving operational excellence and sustaining competitive advantage in the semiconductor industry. Why KPIs matter in semiconductor manufacturing. In semiconductor manufacturing, KPIs play a critical role in driving performance across 3 key areas: cost control, quality assurance, and continuous improvement. For cost control, KPIs help identify major cost drivers, allowing teams to allocate resources more efficiently and reduce waste. This data-centric approach leads to better decision-making and supports sustainable cost reduction. Quality assurance relies on KPIs to monitor defect rates, ensure product consistency, and maintain strict adherence to specifications. With 99% quality consistency achievable, manufacturers can meet customer demands and compliance standards with confidence. KPIs also support continuous improvement by enabling data-driven decisions, driving process optimization, and setting benchmarks for performance. Real-time monitoring, available 24/7, helps detect problems 85% faster and offers up to 30% in cost reduction potential. Ultimately, KPIs transform raw data into actionable insights, forming a solid foundation for achieving excellence through ongoing measurement and improvement. Overall equipment effectiveness. Overall equipment effectiveness, or OEE, is a core manufacturing KPI that evaluates how efficiently equipment is utilized during planned production time. It represents the gold standard for assessing equipment performance and forms the foundation of lean manufacturing excellence. OEE is calculated by multiplying 3 components: availability, performance, and quality. Availability reflects the percentage of scheduled time that the equipment is actually running. Performance measures how fast the equipment operates compared to its maximum speed. Quality evaluates the proportion of good units produced without defects. Together, these dimensions offer a comprehensive view of equipment effectiveness. A world-class OEE score is 85%, indicating exceptional operational performance. A typical OEE is around 60%, while 40% or below is considered poor and suggests significant losses in availability, speed, or quality. By tracking OEE, manufacturers can uncover inefficiencies, benchmark performance, and take targeted actions to improve productivity. OEE, Overall Equipment Effectiveness, the three components. Overall equipment. Effectiveness is calculated by combining three core components: availability, performance, and quality. Each one captures a different dimension of equipment efficiency. Availability is calculated as runtime divided by plan time, or A/RT/PT. It measures how often the equipment is running as scheduled and accounts for downtime due to setup, changeovers, or equipment failures. Performance, represented by P/IRMR, is the ratio of the ideal rate to the actual rate. It reveals losses caused by reduced speed, minor stops, or short interruptions. Quality is calculated as Q, GP, TP, or good parts divided by total parts. This metric tracks product integrity by measuring the defect rate, rework required, and scrap levels. Each component provides insight into where losses are occurring. By improving availability, performance, and quality, manufacturers can significantly boost their overall OEE score and operational effectiveness. Core manufacturing KPIs, Overall Equipment Effectiveness. Overall Equipment Effectiveness, or OEE, is a key performance indicator in manufacturing that drives continuous improvement. It begins by identifying losses, pinpointing specific areas where production is falling short, such as unplanned downtime, slow cycles, or quality defects. Once these losses are identified, benchmarking comes into play. Benchmarking allows manufacturers to compare performance across different machines, lines, or even facilities. This comparison highlights underperforming areas and sets realistic improvement targets. Next, OEE helps prioritize actions by focusing resources and efforts on the areas with the greatest potential for gain. This ensures that improvement strategies are data-driven and targeted. Finally, these actions drive results. Improvements are measurable, often leading to significant productivity gains. OEE operates through three key components: availability, performance, and quality. These metrics collectively form the foundation for lean manufacturing excellence and operational efficiency. Yield rate and cycle time. Yield rate and cycle time are two essential KPIs that provide insight into both the quality and speed of production. Yield rate is a quality output measurement calculated by dividing the number of good units by total units produced and multiplying by 100. A 95% yield is considered excellent, 85% is good, and 75% signals that improvement is needed. High yield rates reduce waste and rework, which lowers costs, increases customer satisfaction, and enhances process efficiency. Cycle time, on the other hand, measures production speed by calculating the difference between the end time and the start time of a process. A cycle time of 2 hours is fast, 4 hours is standard, and 8 hours is slow. Lower cycle times increase throughput, help meet delivery deadlines, and improve capacity utilization. Together, yield rate and cycle time drive operational efficiency and production performance across the manufacturing line. The performance relationship. Achieving optimal production efficiency requires balancing two critical KPIs: high yield and low cycle time. When the yield rate is 95% or higher, there is significantly less rework and waste, which enhances quality and reduces costs. Simultaneously, a low cycle time, such as 2 hours, means faster production and increased throughput. Together, these two metrics lead to optimal efficiency, delivering maximum output with minimum delays and defects. The key insight here is that high yield combined with low cycle time equals maximum profitability. To sustain this performance, several improvement strategies are vital. First, continuously monitor both yield and cycle time in real time. Then, identify root causes behind defects or production delays. Next, optimize process parameters and standard operating procedures. Finally, iterate through continuous improvement cycles. By balancing quality and speed, manufacturers drive success. Remember, quality multiplied by speed equals sustainable performance and long-term profitability. Throughput and equipment efficiency. Maximizing production capacity relies on three key equipment performance KPIs: throughput, utilization, and reliability. Throughput measures how many units are produced per unit of time. For example, a throughput of 150 wafers per hour reflects the system's current output rate. This metric helps gauge production capacity, time efficiency, and where bottlenecks may exist. Utilization represents how effectively equipment is used relative to its total available capacity. A 78% utilization rate means the equipment is being used most of the time, but there is still room for increased productivity. High utilization signals better resource efficiency and lower idle times. Reliability focuses on uptime metrics, including mean time between failures, or MTBF, which is 240 hours, and mean time to repair, or MTTR, currently 3.5 hours. Equipment availability is at 98.5%, which is excellent. These figures help assess operational stability and identify areas for preventive maintenance improvements to minimize unplanned downtime. Performance benchmarks. Performance benchmarks help manufacturers gauge equipment efficiency against industry standards. Three tiers of performance are commonly used: world-class at 85% efficiency or higher, industry average at 65%, and needs improvement at 45% or lower. These benchmarks serve as key indicators for identifying whether equipment is meeting its potential or if action is required. The bar chart compares current values against targets across 5 metrics: throughput, utilization, MTBF, MTTR, and availability. For example, the current MTBF is below target, while utilization is also lagging, indicating room for improvement. To close these performance gaps, 4 core optimization strategies should be employed. Preventive maintenance helps minimize unplanned downtime. Real-time monitoring enables continuous performance tracking. Process optimization focuses on eliminating bottlenecks. Finally, operator training enhances skill levels, enabling more consistent and efficient operation. Remember, overall efficiency is the product of throughput, utilization, and reliability. Each element must be optimized to maximize equipment performance. Quality and defect KPIs. Quality and defect. Key performance indicators, KPIs, are crucial indicators for maintaining zero-defect manufacturing excellence. First, let's examine first-pass yield, which reflects the percentage of good units produced without needing rework. It's calculated by dividing good units by total input. The current performance is 94.2%, which is higher than the industry average of 91%, but still 3.8% below the target of 98% or more. This signals a need for improvement. Next, the defect rate is a critical measure of quality, reported in parts per million. It's calculated as defects divided by total units, multiplied by 1 million. The current defect rate is 580 parts per million. For reference, Six Sigma excellence is 3.4 parts per million, and world-class performance is 100 parts per million. So, at 580 parts per million, the status is marked as improve. Lastly, the rework rate shows 5.8% of production requires correction. This results in a $125K monthly cost and 240 hours of lost time. The goal is to reduce rework to under 2%. Quality and defect KPIs. Trends and cost of poor quality. Over the past 6 months, the quality trend has shown a 12% improvement, indicating solid progress towards zero-defect manufacturing. The first-pass yield, shown in green, has steadily risen each month, climbing from just below 89% in January to above 94% in August. At the same time, the defect rate, shown in red, has significantly declined from around 850 parts per million in January to approximately 580 parts per million in August. This dual improvement is a positive signal that our quality initiatives are working. However, the cost of poor quality remains high. Scrap and rework account for $450,000 annually, which is 45% of total quality costs. Inspection and testing follow, costing $280,000 or 28%. Customer returns cost $270,000, representing 27% of the total. Combined, these add up to $1.2 million annually, equivalent to 4.2% of company revenue. Reducing these costs can significantly impact profitability and operational efficiency. Quality and defect KPIs, top defect categories, and improvement roadmap. Understanding the top defect categories is essential for driving effective quality improvements. The most significant category is layer defects, contributing to 32% of all issues, often tied to deposition inconsistencies or contamination. Next are dimension issues at 24%, which typically result from process drift or inaccurate calibration. Surface defects account for 18%, often due to handling or cleaning failures. Electrical faults contribute 16%, which could stem from material inconsistencies or patterning errors. Finally, other issues represent 10%, encompassing all other minor or sporadic defect types. To tackle these challenges, a robust quality improvement roadmap is essential. Root cause analysis uses tools like statistical process control and the 5 Why method to identify underlying issues. Automated inspection leverages AI to detect defects with speed and precision. Operator training builds quality awareness and enhances skills. And process standardization uses poka-yoke techniques to prevent errors before they occur. The guiding principle remains: prevention is better than detection and far better than correction. Cost and financial KPIs, maximizing profitability and ROI. Cost and financial KPIs provide critical insight into manufacturing efficiency and return on investment. Starting with cost per unit, the current value is $425 per wafer. This figure is calculated by dividing total cost by the number of units produced. While better than the industry average of $450, it remains higher than the internal target of $380. This reflects a 5.6% improvement opportunity to close the gap and enhance competitiveness. Next, ROI, or return on investment, is a vital measure of financial performance. Using the formula gain minus cost divided by cost, the annual ROI is 18.5%. When broken down further, equipment ROI is at 22.3%, while process ROI is at 15.7%. The overall payback period stands at 4.2 years, which helps gauge how quickly investments return value. Lastly, the cost ratio represents manufacturing cost as a percentage of revenue, currently at 68%. This is better than the industry average of 72%, but not yet at the best-in-class level of 62%. Bridging that gap could unlock a $2.4 million opportunity for the business. Cost and financial KPIs, breakdown, trends, and detailed analysis. A clear understanding of cost structure is key to managing profitability. The total manufacturing cost is $8.5 million per month, broken down across 5 major categories. Equipment costs lead at $3.2 million, making up 38% of the total. Labor follows at $2.1 million or 25%. Materials account for $1.7 million or 20%. Energy costs contribute $1.0 million, equating to 12%, while maintenance is the lowest at $0.5 million or 5%. Looking at cost per wafer, the breakdown is as follows: $160 for equipment, $105 for labor, $85 for materials, $50 for energy, and $25 for maintenance. The cost trend analysis shows an encouraging 8% cost reduction achieved over the year. Both cost per unit and manufacturing cost ratio have declined steadily from Q1 to Q4, signaling improved efficiency. These insights are crucial for targeting high-impact areas and ensuring strategic cost control, which directly boosts overall ROI and competitiveness. Cost and financial KPIs. Maximizing profitability and return on investment requires a strong focus on cost and financial KPIs. Key strategies include lean manufacturing, which eliminates waste and improves flow, offering 8 to 12% in potential savings. By streamlining operations and reducing inefficiencies, businesses become more agile and cost-effective. Automation plays a significant role by reducing labor costs and minimizing errors, delivering between 15 and 20% in savings. This includes the use of robotics, AI, and other digital tools. Energy efficiency contributes 10 to 15% in savings by integrating smart systems and process optimizations to cut down on utility expenses. Finally, supplier optimization provides another 5 to 8% in savings by leveraging strategic partnerships and negotiations to secure better terms and pricing. Remember, cost control drives profitability, and it's essential to continually measure, analyze, and optimize. ROI is calculated as revenue minus costs divided by investment. Safety and environmental KPIs. Protecting people and the planet is essential to achieving sustainable manufacturing excellence. Key performance indicators in safety and environmental areas provide a clear measure of progress. The incident rate stands at 0.8 OSHA recordable cases per 200,000 hours, above the target of less than 0.5. Currently, the site has maintained 45 consecutive safe days. In terms of energy use, each wafer consumes 125 kilowatt hours. While this is above the target of 115, it represents a 10.7% improvement from the baseline of 140. For waste rate, 0.85 kilograms of waste are generated per wafer. Of this, 78% is recycled, 12% is hazardous, and 10% ends up in landfill. Lastly, carbon emissions are at 45.2 kilograms of CO2 per wafer. While higher than the 2025 target of 35.0, there's been an 18% reduction overall, with 42% of the energy now coming from renewable sources. Sustainability trends and compliance status. Tracking both sustainability trends and compliance status is vital for long-term environmental responsibility and workplace safety. Over the past 5 years, there's been a 25% improvement in the environmental footprint. The environmental score has steadily increased, indicating better sustainability practices. The safety score is also rising, reflecting a stronger culture of safety. In contrast, the energy efficiency index has been declining, highlighting an area that may require corrective actions. On the compliance side, all environmental permits are 100% current and in full compliance. Safety training completion is at 92%, meaning 8% of employees still need to renew their certification. Water discharge metrics are within legal regulatory limits at 95% compliance. However, chemical storage is flagged for an audit, with an inspection scheduled in Q2. Proactive measures here are necessary to ensure safe chemical handling and regulatory alignment. Environmental performance. Environmental performance is central to protecting both people and the planet. Water use currently stands at 2.8 liters per wafer, which is 15% better than target benchmarks. Air emissions are well within acceptable limits, measured at 23 parts per million. Renewable energy usage has risen to 68%, reflecting a 12% year-over-year improvement. Additionally, 85% of waste is successfully diverted from landfills, reducing environmental burden. However, hazardous material generation is at 0.12 kilograms per wafer and must be monitored closely. Average temperature rise is noted at 22 degrees Celsius, indicating a heat island effect that requires further investigation. The 2025 Sustainability Roadmap outlines key goals: achieving zero incidents through enhanced safety protocols, transitioning to 100% renewable energy, reducing carbon emissions by 50% by 2025, and advancing a circular economy with 95% waste diversion. The commitment to safety, sustainability, and operational excellence ensures long-term impact for people, planet, and profit. Implementation and success. Turning KPI insights into actionable success requires a structured framework. The first step is to define KPIs clearly. This means setting specific targets, aligning them with broader business goals, and establishing a clear sense of ownership. Defining KPIs involves understanding the baseline, setting measurable targets, and assigning responsibility. Next is the measure phase, where real-time data collection and automated dashboards help track performance. Reliable systems, smart tools, and consistent data frequency are crucial to ensure accuracy and visibility. Once data is gathered, the next phase is to analyze. Here, root cause analysis and trend identification come into play. Teams seek insights, look for recurring patterns, and identify performance gaps. Finally, step 4 is to improve. Action plans are executed, results are closely monitored, and processes are continuously optimized. Through execution, monitoring, and iteration, organizations drive sustainable performance and KPI excellence. Critical KPI categories. To successfully turn KPI insights into action, it's essential to focus on critical KPI categories that directly impact operations. These include OEE, or Overall Equipment Effectiveness, which stands at 85% and reflects how well equipment is utilized. Yield, representing production success, is at 92%, indicating high-quality output. The cycle time for processes is 24 hours, emphasizing time efficiency. Throughput is measured at 850 units per day, showing how much product is produced. Cost per unit is 425, an important financial metric for profitability. Safety is also critical, with an incident rate of 0.8 per 200,000 hours. To support these KPIs, best practices include real-time data collection, cross-functional accountability, regular reviews, automated alerts, benchmarking, and training. Implementing these practices can lead to a 15 to 25% improvement in ROI, as shown in the impact graph. Strong KPI programs enable measurable gains across safety, quality, and cost. Start your KPI journey today. Transforming semiconductor manufacturing begins with data-driven insights and a structured KPI journey. In Phase 1, the focus is on selecting 3 to 5 core KPIs that matter most to your operations. These should be aligned with business objectives, and baseline metrics must be clearly established to serve as a benchmark for future performance. Moving into Phase 2, organizations should deploy robust monitoring systems and train their teams to ensure accurate data collection and interpretation. This phase builds the foundation for informed decision-making. Phase 3 is about optimizing and expanding, scaling what works, and applying lessons learned across more functions and departments. The key message is, what gets measured gets managed. Start small, think big, move fast, and measure everything. Excellence is not a final destination. It's a continuous journey of improvement, refinement, and sustainable success. Thank you, and consider what your next step will be.